Well, hello. Good just afternoon, and thank you for joining us. I'm Greg Heston. I teach in the physics department and serve as Associate Director of Science Ed. And on behalf of the Harvard Division of Science, the Harvard Bookstore, and Harvard Library, I'm very excited to welcome you to this very exciting science book talk with Professor Andrew Pontzen, and he'll be discussing his book, The Universe in a Box, Simulations and the Quest to Code the Cosmos. But before we get into that, if you want to learn a little bit more about the other talks in this series, you can check out our website. Just Google Harvard Science Book Talks. And if you want to watch previous talks, you can just search on YouTube for the same thing, Harvard Science Book Talks. And we have some upcoming great events as well. We have Jim Al-Khalili talking about the joy of science. And we also will have in the coming months, Eric Hole, who will be talking about the world behind the world, consciousness, free will, and the limits of science. And so there'll be more information on those soon. But today we are very excited to have Professor Andrew Pontzen, who's a professor of cosmology at the University of College London. He's written for New Scientist, BBC Sky and Night, and BBC Focus. He's lectured at the Royal Institution and has been featured as an expert on PBS's Nova and the Discovery Channel's How the Universe Works and other shows. And his research spans cosmology, physics, computation, and much of it involves simulations like what we'll hear about tonight. Or today. It's tonight for you, Andrew, who are in London. And he'll be discussing his book with Çağan Şengül, who received his PhD here at Harvard this past May, where he worked on strong gravitational lensing under the supervision of Professor Cora Dvorkin. And he's now heading off to University of Pittsburgh as a Samuel P. Langley Postdoctoral Fellow. And his research focuses primarily on the dynamics of dark matter. And he's particularly interested in investigating cosmological and astrophysical observations to uncover potential and evidence of physics beyond the standard model. And so today they'll be discussing Andrew's book, The Universe in a Box. But I just wanted to say, Philip Pullman, who's the author of the trilogy, His Dark Materials, said that this book is a truly excellent exposition of a fascinating, little understood, and very important scientific activity. I was enlightened, amazed, and profoundly impressed. I have seldom seen a book so clear, so vivid, and so full of, well, interesting things, which we are about to hear about. But before we do, I want to say, as you're hearing these interesting things, feel free to drop any questions that you have into the Q&A. There's a little Q&A button on your Zoom at the bottom. And toward the end, Çağan and Andrew will discuss some of those questions that come in. And also, right after we start here, I'm going to drop a link to purchasing the book, if you so wish, into the chat. So with all of that, Andrew, I will let you take it away.
Oh, thank you so much. That was a really generous introduction. I'm going to try and share some slides for a few minutes. Let me just check this is working. Hopefully this has come up for you. So there is the book. If just in case anybody is joining the webinar from the UK, I've put a small version of the cover of the UK version. It looks very different here in the UK, but it's the same book inside. The point of The Universe in a Box is kind of to introduce this idea of how we simulate the whole universe. And I wanted it to be a book that was for everyone, that didn't assume any advanced knowledge of cosmology. So let's start from what you can actually see in the night sky. And you know, if you go somewhere in a city and look at the night sky, it can just look like there's a few stars up there, which is nice. But it's maybe not quite as impressive as what we know is actually there. Because if you go somewhere a bit darker and you allow your eyes to start adjusting so that they can see much fainter objects, then slowly your eyes will start picking out more and more stars until eventually with the naked eye you can actually see a few thousand stars. And those stars are all part of what we call the Milky Way galaxy. So the Milky Way galaxy is, again, something that you can see with your eyes. If you go somewhere that's dark enough and you have the patience to let your eyes adjust, then you will start to see a kind of faint band of light like this splitting the sky. And that's what we call the Milky Way. In fact, that band of light is just created by a huge number of stars beyond the individual ones that you can see. So more or less, those few thousand stars that you can see with your naked eye are the close, bright ones, but there's a kind of sea of stars out there in our Milky Way, hundreds of billions of stars, in fact. And what you see of those is just this kind of milky band crossing the sky, where the combined light from all of those stars shows you that band across the sky, because the galaxy itself is kind of in a flat disk. And one of the most remarkable things to me from recent years in astronomy is that it turns out that many, perhaps most of these hundreds of billions of stars have planets. There's been a remarkable discovery that has happened just in the time I've been working in astronomy. And it is entirely possible that there will be many terrestrial planets out there. So, you know, somehow appreciating the scale of this is already quite hard. But we're only at the beginning in terms of what cosmology and the simulations that I'm going to talk about actually probe. So our galaxy, the Milky Way, has a partner galaxy that we call Andromeda. This is a picture of Andromeda. This is something else. You can actually see this with the naked eye as well, if you know where to look. It's quite large, several times bigger than the size of the moon on the sky. But it's very faint because it's far away. It is actually a galaxy all of its own. So this Andromeda galaxy has its own hundreds of billions of stars, and it's just far enough away that they just turn into a kind of smear on our night sky. But that is also just the beginning, just the cosmic doorstep, because this is just two of many, many galaxies out in the universe. When we point telescopes out into the universe, you can find many more. And if you have a few $1 billion spare, then you can make some telescope as good as the James Webb Space Telescope. And what I'm showing you here is a picture that was released to the public just maybe a month ago from the James Webb Space Telescope. And specifically the JADES team, who are working on early data from the James Webb Space Telescope. And what you're looking at here is a tiny, tiny patch of our night sky. It is far, far smaller than the extent of the moon, maybe about a fifth of the diameter of the moon. But the James Webb Space Telescope was pointed into this patch of the sky. And because it's very sensitive, it has a very large mirror out there in space, it's able to pick up very faint, it's kind of sharp images of very faint, very distant objects. And all of the things that you see here right now, they're all galaxies far beyond our own. And that all of those are just crammed into that teeny tiny patch of the sky. So if you crunch the numbers and you try to extrapolate to how many galaxies are there in the universe as a whole, you come up with a number of perhaps trillions. I mean, we don't actually know, because we don't know the full extent of the universe, but in terms of the volume that we can actually see, in principle, we could probably find trillions of galaxies. Now that's not the end of the story, because the galaxies aren't just scattered at random. This picture makes it look a little bit like the galaxies are just peppered through space, but actually we know that on larger scales still, there's a pattern to the way that the galaxies are arranged in the universe. In fact, one of the first systematic surveys of the sky to reveal this was conducted at Harvard. The kind of patterns that it revealed, this is actually from a computer simulation, but it gives you the right idea. When you look far out into space and you see where the galaxies are, they are organized into what we call the cosmic web. So this is now on such large scales that every tiny dot of light you see here is an individual galaxy. And remember, a typical galaxy has those hundreds of billions of stars in it. So we are looking on insanely large scales here. But you can measure this and you can reproduce it in computer simulations as well. The universe is structured on these insanely large scales. So the question that we really have as cosmologists, I suppose, is twofold. First of all, how did the universe come to be structured in this way? How is it that the universe has these galaxies, which are islands, kind of fizzing with stars and planets and perhaps life, we don't know, surrounded by large empty spaces, but then on even larger scales, the actual pattern of the galaxies themselves is arranged into some kind of coherent structure on these gargantuan scales. How did that happen? And I guess we have another question, which is, how can we relate to it? What does it mean for us here on Earth to see these patterns? How does it relate to the story of our own solar system and the sun and the Earth? And it turns out computer simulations are a great way to get to grips with these kind of questions. But they also reveal one last surprising fact about the composition of our universe, which is that everything that I've shown you so far is still really the tip of the iceberg. All of these visible materials, the things that we can see directly through telescopes, comprise, as far as we can tell, just 5% of the total mass and energy budget of the universe, whereas the remaining 95% of the universe is made out of materials which, at the moment, we're unable to probe in any laboratory. This does sound a little crazy. I mean, I always felt like when I was an undergraduate learning this stuff, it felt a little bit like, well, people are just making stuff up to try and make sense of something that otherwise wouldn't make sense. But it turns out that this kind of missing 95% of the universe, which itself decomposes into two different substances, which we call dark matter and dark energy, are not just crucial to explaining everything that I've shown you so far, but they've actually been very predictive. So that is to say that, especially when you pair them with simulations, when you program the ideas of these substances, dark matter, which is an extra material in the universe that isn't seen directly, but that makes its presence felt through gravity. So it's able to pull things around and pull them into different shapes and make them behave in ways other than what they would otherwise do. So there's dark matter, and there's also dark energy, which seems to be pushing on very large scales, pushing the universe apart. Both of those ideas have been very predictive, and simulations have played a very large role in enabling us to go from the basic idea of these extra materials to making quite firm predictions about what those should do in relation to what we can actually see through telescopes. So what I wanted to use the rest of these few minutes to show you is what that actually looks like within a typical simulation. So I'm going to show you an animation of how a typical simulation proceeds. Now, there are multiple ways that you can bring these to life, that you can render these into graphics. What I'm going to do here for you is show you the universe from a very early age, when we know that the universe was much, much smaller than it is today, through to the present day. And the universe that I'm simulating at the moment just occupies a tiny dot in the center of the screen. But when I start time running, you'll find that you see the universe expand. This is something that's been programmed into the computer. It's been told that our universe is an expanding universe. And you'll see that there's kind of clouds of material now on your screen. I've colored them green. That's because, well, first of all, I can choose whatever color, of course, I want the computer to use. But the material that you're seeing on the screen right now is actually dark matter inside the computer universe. So I chose to color that green because it's a useful reminder that in reality, we would never see this stuff through a telescope. The stuff you're seeing on the screen right now would be invisible if you could somehow look at this virtual universe through a telescope. But already about 1.7 billion years into the history of the universe, it's going to be about 14 billion years old in total, already you can see that this universe has not just expanded, but it's formed something like that cosmic web that I was showing you a moment ago. Now, at the moment, you're just seeing it in dark matter, but the simulation is also able to make predictions for what this universe would look like in terms of the luminous matter that we can actually see through telescopes. So I can switch to that view now, and it looks more like this. So what this simulation is able to show us is that it is the gravitational force coming from the dark matter that sculpts the cosmic web that you're now seeing in the kind of visible light of the universe. By the way, I'm sort of artificially spinning this universe around so that you can see the 3D structure. Of course, when we measure the real universe, we do just get one view of it. But from a virtual universe, we can kind of spin it around and take a look at what it looks like. So this is a frozen snapshot of what the universe looks like at this moment. And we can actually fly through this virtual universe to see a bit more detail. All of those dots that you can see on the screen, they are actually little mini galaxies that are in the process of forming. We'll fly right through one now. You saw all of those stars go past. The simulation enables you to study this process via which the dark matter starts gathering materials together and gathering gas together in particular, and then the gas then turns into stars. You're seeing here, I've switched back on the dark matter to show you that it's providing a kind of scaffolding for this whole process. And then finally, if I restart time, you can now see this process go forward, now on a much sort of zoomed in level, so that we're looking at one particular galaxy getting built. And again, due to the dark matter, there is a whole process of merging where a bunch of small galaxies that are formed in the early universe, over time, they merge together to build bigger and bigger galaxies, which, if you fast forward all the way to the present day, you can end up with kind of swirling masses of gas and stars. And if you fly into one of these and take a look at what it would look like from our position, about sort of halfway out from the middle of a galaxy, then it does look a little bit like the night sky as we see it for real from here on Earth. So this is the kind of stuff that we're trying to learn about from simulations. Now, obviously, a lot goes into performing these simulations, and maybe in the discussion in a moment, we'll get to talk a bit about that and about the kind of combination of physics, but also some stuff that kind of goes a bit beyond physics, or we have to do a bit of guesswork to help the computer along the way. And we'll maybe get a chance to talk about that in a moment. But just before I wrap up my little segment, I wanted to mention that, you know, another thing that I really wanted to do with the book was to show that these ideas don't just drop out of the sky. They come from a sustained effort from a large number of people. And I think one of the joys of writing the book was discovering some of these stories. Now, going all the way back to the first ideas around computers, people like Charles Babbage and Ada Lovelace. I mean, Ada Lovelace in particular wrote extensively about how computers might be used if they came to fruition. This was in the 19th century, long before computers were actually built for real. But she wrote a really beautiful description of what essentially a simulation is, saying, she said that those who view mathematical science not merely as a vast body of abstract and immutable truths will regard with especial interest all that can tend to facilitate the translation of its principles into explicit practical forms. And it's effectively, it's that translation of a set of principles into something that's practical that we're doing here. And maybe to make it even more practical, you know, the same kind of things that we're doing in cosmology are also at the heart of what happens in meteorology. So here's a brilliant character from the book, Lewis Fry Richardson, who attempted to do simulations of meteorology to make weather forecasts before computers were even available. He was trying to do this by hand using a kind of, it looked like a kind of giant spreadsheet he was filling in, doing loads of calculations by hand in order to do that exercise of turning the kind of theoretical physics into something really practical, where you could really practically understand what was going on. All the way through to people like Beatrice Tinsley, who performed the first galaxy formation simulations in the late 1960s. And indeed, since this is the Harvard bookstore, I thought I would mention another story in the book, work that came out of Harvard by Tiziana Di Matteo and her collaborators. This is a 2005 piece of work, one of the first pieces of work to really show how simulations could let us understand the relationship between galaxies and their central black holes. It turns out that there's a very deep relationship between the life of a galaxy and the fact that actually all galaxies, as far as we can tell, host huge black holes. And this work was one of the first to dive into that. So I hope I've given you a little bit of a taste of what this book is all about. But right now, I guess I'm looking forward to diving into a bit more of a conversation with Çağan.
Yes, Andrew, thank you for that great presentation, and thank you for this book. It was a great pleasure to read this over the past week and read your book. And I'm glad that finally there's a pop science book that explains the physics of simulations and how they're used in cosmology. So whenever my friends ask me questions about cosmology, simulations were one of the trickiest things that I had trouble explaining to them. So now I can point them to your book, and they can learn all about it. I would like to ask you a question first about the analogy between meteorology and the simulations lead to meteorological predictions and cosmology. So there are great parallels, as you mentioned in the book, of the way we try to predict the weather with simulations and the way we run universe simulations in boxes in science. But with weather predictions, we are generally interested in a particular weather front affecting a particular area. So in that sense, those things are very specific, and we're interested in that because the farmer's output depends on it, a lot of economic impact depends on it, our lives depend on it. But with cosmology, we are more interested in the phenomenon, trying to understand the general principles that brought us here. So this difference, how does that affect the way you run simulations?
Yeah, so I think that's absolutely right, that there's a crucial difference there. And in this sense, I think in a way, what we're doing in running cosmological simulations is often a bit more like climate science rather than weather simulation. Mm-hmm. So weather forecasting is clearly an incredibly important application of simulation technology, and it's where a lot of the ideas that we now lean on came from originally. Including the fact that our atmosphere is made out of gas. The gas moves around according to the laws of fluid dynamics. And so the way that you then go about putting those laws onto a computer, getting it to do this, making a practical prediction from them is similar in that respect. But yes, you're right that if you then go and say, well, what kind of predictions do you make? We're not in the business of predicting directly exactly what's going to be seen tomorrow, say. For a couple of reasons. One, the universe only changes on very slow timescales by and large. That the weather changes daily, but the night sky doesn't. There are a few exceptions to that, but by and large, things are changing very slowly. And there's a second reason, I suppose, which is that with weather forecasting, we can more or less get as much information as we would like about what we call the initial conditions. So that's to say that I suppose the weather that we experience today has been affected by what the weather was like yesterday. And what's going on today is really important for what will happen tomorrow. And so you can gather information from satellites and from weather stations and feed all of that in to the simulation. And we can't really do that for the universe. We have a lot of information about what the early universe was like, but that's not quite the same as knowing precisely what the conditions were like, in the bits of the universe that we're interested in. So we have sort of general information about what the universe was like, rather than very specific information about exactly what it was like in one particular location or another. And so for that reason, it becomes a bit more like a climate simulation. And a climate simulation is like it's extrapolating a weather forecast to very large timescales, but doing it to get trends and patterns rather than to make very specific predictions about particular weather events. And I think, you know, that's the way I would think about our cosmological simulations. They are making predictions about trends and patterns. And sometimes those predictions are looser than we might like them to be, but they're predictions nonetheless. Then we can go and kind of look at how do we measure those trends and patterns against real data. But it's very much about that kind of big picture trends rather than very specific things.
Yeah, one idea that I also mentioned in the book is the idea that with the weather predictions, how chaos builds up and prevents you from predicting the weather more than 10 days into the future. It becomes more and more inaccurate as these small uncertainties in your measurements of the conditions, initial conditions, accumulate. In a sense, I'm curious. It's really fascinating that even though there's this chaos that prevents you from knowing exactly what's going to happen in the future, there's still this fascinating and magical aspects of simulations that enable you to make general predictions like climate about the future, even though you can't know the weather 20 days from now. You know, if you keep emitting carbon into the atmosphere, the Earth will get warmer and warmer. So that is something that we can more robustly know.
Yeah, I mean, I think that is a very fascinating topic, and being able to be clear about what you can confidently predict despite the presence of chaos from what you can't confidently predict is very much the name of the game. And I think, you know, in the cosmological simulation community, we are increasingly getting to grips with this. It's quite a hard problem to look at, but you can do experiments, like numerical experiments, where you do just intentionally change something very small and see it would do this tiny change that it is sort of barely noticeable in its own terms. How does that then build up and affect things later on? And a number of studies have been done of that. And, you know, the typical answer is that it can profoundly change what's happening in an individual place, but the kind of overall patterns that emerge remain the same. This is something, of course, that is very important, as you just said, for climate change science. And Nobel Prizes have been won for demonstrating this property of climate simulations, both empirically and mathematically. It's possible to demonstrate that certain properties will remain predictable. But one of the things that's kind of hard and a continual source of research is to just be really clear about which side of that line do which sets of predictions fall on. So it's a kind of exciting and continually evolving area.
Yeah, last thing I want to ask you about the parallel between weather and climate and cosmological simulations is that the idea that even though you cannot, sorry, just a second. The idea that even though you cannot go down to the smallest scales, meaning you cannot actually track every single air molecule in Earth's atmosphere, there is still feasible to run simulations because of the idea that you mentioned in the book of subgrid physics. So it's a little bit technical, but I'll let you explain to the audience of how this becomes possible, even though we can't track every single molecule, by implementing clever rules, both in astrophysics and cosmology, about how gas and dark matter behaves in scales that are below the resolution of the simulation. You can make these really realistic predictions.
Yeah, so I think, you know, weather offers a great example. And if you think about a kind of hot, humid day, and you look up at the sky, you start to see clouds start to form. They're initially they're very small, like they may, you know, they can be like a mile across or something, or even smaller than that. those clouds are profoundly important to what happens next. First of all, they will either rain on you or they won't, and they'll either unleash lightning or they won't. But more than that, those clouds might change the temperature as well, because once they're there, they're reflecting the sunlight back out into the cosmos, and preventing the heat from reaching the ground. So they're changing the temperature, and that changes the pressure, and that changes the winds. And so, all of this stuff links together. So you can't afford to ignore those clouds. And yet they're so small on the scale of the Earth, which is what you're trying to model the weather across. They're so small that it's really hard to capture them in any meaningful way. And they're chaotic as well, in the way we were just discussing, that a tiny change that you couldn't possibly know about in advance could completely exactly a cloud forms. So what do? Well, you have to invent some set of rules. And the rules are typically based on a number of things. They're partially based on some physics. We know that there is well-established physics about convection and so on that tells us when clouds are likely to form, even if not precisely when they'll form. They're partially then calibrated on experience and on past weather to really understand, okay, there's no way we can get every last physical detail of this right. So let's just put down a kind of reasonable guess for when clouds will form, and then calibrate it based on the empirical data that we have available. And then you can put that into a simulation, and it actually works surprisingly well. And it won't tell you like very fine scale detail. Of course, there's a limit to how good it can be, but in a sense, it's the same point, that despite the fact that you're getting the details wrong, which we knew anyway, we would get them wrong due to chaos, somehow the picture that emerges can still be right. In a cosmological setting, we're doing similar sorts of things for the formation of stars, say. That the fact is that the universe was born without any stars in it. All the stars have formed since the universe was born. And so understanding why and where they formed is a crucial part of what we do. But stars are actually very, very tiny compared to the kind of scales that I've just been talking about. Even compared to a single galaxy, they're minuscule. So we do something very similar. We have to use some inspiration from physics. We have to calibrate it based on things that we know happen in the real universe. And there's a kind of collection of ideas that go into that, which I think you can see it as in one of two ways. Some people view it negatively as it's being a bit of a fudge. Like we can't really do this exercise, and we're having to just do what we can, but it's not really reproducing the universe. That's one way to view it. I think another way to view it is to say, sure, we were never going to reproduce the universe. That would be a crazy goal. We're trying to learn something new about how the universe works. And you can definitely do that, right? Even if you don't know every detail, you can get these overall patterns and see how the overall patterns reflect what you're putting in about these very hard to model small scales and so on. So for me, it's almost like it's an exciting aspect of what we do.
How do we know? So when we are tuning to match reality, right? You're tuning the subgrid rules, but there has to be a balance between how much you're tuning to the reality versus how much you're trying to explain reality with simulations that are as generic as possible, as much from the first principles, physical laws as possible. But as you mentioned, there's also the practicality aspect of it. Without assigning these subgrid rules, you can't make any predictions. So I guess, as you mentioned in the book, it's more of the art of running simulations is finding this balance. How do we go about doing this reasonably?
Yeah. I think the short answer is it's incredibly difficult and very controversial. I think is, you've got right to the core of where these things can be most controversial. And it's possible, though, to get too pessimistic about this. I think, it's sort of a bit like what I was saying a moment ago. one possible reaction to this is, we're never going to really understand what's a genuine prediction and untangle that from what we just put in by hand. I don't think that's necessarily the case. I think different people have different ways of approaching this, but you can do things where you quite carefully kind of say, I'm going to calibrate on these things. So let's say it might be the range of different brightnesses and sizes of galaxies that you have in the universe observed today. And you say, I know that as I change the details of how stars form, that's going to change. So I know that I won't exactly be able to predict those things. I'm going to calibrate on those things. But then I'm going to test whether that then makes correct predictions for what happens in the ancient universe. I mean, one of the great gifts that astronomy gives us is the ability to see the ancient universe as well as the modern universe, just because if you look far enough away, it takes a long time for the light to reach you. Light is going very fast, but like anything, the further it has to travel, the longer it takes to get there. So when we look to very distant parts of the universe, we're looking back in time. So that's one example of how you might do this. You can say, I will allow myself to calibrate things based on what we see of the universe today until that comes out roughly correct. But then I'll see, am I making successful extrapolations about what was happening in the past? So that's one example of a kind of approach that you can take with this. But yeah, it is hard, but I think it's also exciting.
In a sense, that there seems to be a parallel between that idea of subgrid rules being tuned for a particular thing ends up explaining things that they were not being tuned for or considered for. Like dark matter, for instance, the idea of dark matter was first thought of to reconcile the idea that stars were rotating in galaxies a little too fast than what is predicted from just the visible matter. But dark matter ended up explaining a lot more things in the universe. So then that gave us the confidence of its existence more and more. So in a sense that with simulations, the recipe of the simulations, you become more and more sure the more independent things that it starts explaining and predicting. No?
That's right. And I think dark matter is a great example, because very often when we're explaining this, we draw attention to things like the rotation curves of galaxies, which, as you're saying, the outer parts of galaxies seem to spin too fast. Something needs to be holding those galaxies together. And that's one of the first pieces of evidence that something like dark matter might be there, providing extra kind of gravitational glue. But yeah, I mean, I think the thing that's really convincing about dark matter is not that. That is the starting point for dark matter. And then with the help of simulations, dark matter has gone on to make many predictions and explain very, very non-trivial things about our universe, like the cosmic web. It's almost impossible to explain the cosmic web. Well, I mean, I think it probably is impossible to explain the cosmic web without having something like dark matter. But moreover, it kind of was involved right from the start. It made predictions about that right at the same time that the surveys were starting to show that the cosmic web really was there. So we have this strange thing in cosmology that the universe isn't changing very fast over time, but our knowledge of the universe is changing quite fast. So you can make predictions for what we will be able to see through tomorrow's telescopes. And that can kind of give you some confidence that whatever you're putting together with the dark matter and the dark energy and the subgrid rules, it has some meaning to it. Doesn't mean it's literally correct. Like all science, it's all provisional, but it's clearly like a very productive line of exploration. It seems to be taking us towards a much better understanding of the universe overall.
That leads me to my next question, where another utility of simulations, as you mentioned in the book, is that it's not enough to just write down an equation of physics, let's say Einstein's equation for general relativity. It's another thing to fully understand the consequences of the equation. That in fourth chapter where you talk about black holes, that's explained quite nicely, where Einstein writes down his equations, but it's not obvious that the idea of black holes emerges from the equations, but it's not obvious to people, and it takes a very long time for people to accept the idea that these objects must exist as a consequence of the theory. So in a sense, simulations, how essential are simulations in understanding the laws of physics rather than just looking at the equations on paper?
Well, I think they give us a different perspective on the laws of physics. They allow us to understand it in a slightly different way about what do the laws of physics kind of enable to happen in a way that is much harder to get at in paper. So in your example of black holes, it's a great one. I enjoyed finding out about this actually while I was writing the book. You know, how did the idea of black holes actually start to get taken seriously? Mm-hmm. And the answer is simulations actually played a huge role. The simulations were necessary because even if you accept that black holes could exist in principle, in terms of just the maths of it, it's quite another thing to say that they exist for real in the universe. Mm-hmm. And the question became, well, at the end of a life of a star, there's a possibility that when it runs out of nuclear fuel, there's no longer any energy there to create the pressure to hold the star up, and it could collapse in under its own weight. And that would seem to lead to a black hole. But with pencil and paper calculations, it's extremely hard to make any statement about, will that happen for real? Or would it be more likely to be the case that actually, when it starts to collapse, then the nuclear forces that would exist between the nuclei of the atoms that originally made up that star, maybe those nuclear forces will be strong enough to kind of push the whole star back apart. And it really took simulations to show that it can go both ways. So sometimes stars do get pushed back apart, and that's what we call a supernova explosion, where at the end of the life of a massive star. And other times they collapse in, and that nothing can stop them. The nuclear forces, even despite being incredibly strong, won't be strong enough to stop the star from collapsing. It really took simulations to be able to see that, and bringing together what was known about the nuclear forces, which are also very, very complicated. How do nuclear forces really work and behave? That was also, only barely understood, alongside the relativity, which is also, really hard to understand. Bring these together in a computer and kind of get the computer to do the hard work of all the maths that's involved in then crunching that through and seeing these consequences. So I think, simulations do enable us to do stuff that we couldn't do with pencil and paper. And you get to a point where the scale of the calculations the computers are doing are such that it would take such, you can always imagine, well, surely humans could do it given enough time. But, when it gets up to millions of years of human calculation to get one answer, then you realize computers are really doing something genuinely new. And I think it goes all the way back to that Ada Lovelace quote that I gave both in the book and in the little talk, that, translating this into explicit practical forms. And that in itself, that exercise brings quite a lot of surprises along the way and shows that things can behave in ways that we didn't really expect just from looking at the equations.
So do you think even if we reach the holy grail of physics, which is unifying quantum mechanics and general relativity, let's say we have a theory of everything in a final equation. So you think you will probably be still running a lot of simulations, simulating that equation and its consequences to continue doing more science, no? So then...
Yeah, I think that's exactly right. So, obviously it would be very exciting to get a theory of everything that unifies quantum mechanics and gravity and so on. But we already, a lot of where that's important is in the very, very early universe, much, much earlier than what we're simulating. What we are trying to do as cosmologists very often is to trace through from those early moments what happened next. Despite the fact that our theories are incomplete, we can still characterize what came out of the early universe quite well. We have both, enough theory and also observational information about what was going on in the early universe that we can do that. So getting that final theory of everything might not actually change very much in what we're trying to do, which is much more about understanding the story of how things unfold, understanding how different parts of the universe relate to each other, and you know, how galaxies come together and build up their chemical elements and ultimately allow rocky planets and life to evolve. These kind of questions, I think, sit on a slightly different layer of questions. Now, those layers talk to each other. You know, there's dialogue between those layers, and maybe the most obvious place is dark matter. You know, a lot of what we're trying to do with simulations is to understand dark matter at the moment and understand what it could be, and that in turn may feed into our better understanding of particle physics, which eventually feeds into this kind of theory of everything idea. So it's not like they're completely separate, but they are somewhat separated, and they do deal with slightly different sets of issues.
Yeah, before we go into audience Q&A, I would like to ask my final question, which is a little bit more of this about the sci-fi aspect of the book, which is the idea that the reality that we live in could itself be a simulation. You explore this idea really well in the book and talk about how this could be feasible or not unfeasible in different aspects. What's the capacity of being able to simulate an entire universe? How much energy do we need, etc. You also talk about looking for glitches in the simulation and how this wouldn't be in your, I don't want to misquote you, but the idea that like looking for glitches might not be the best of practices, might not be the most scientific of practices, because we could never tell whether something is actually a glitch or some more deeper physics that we don't know yet. So how do you think we should go about trying to research the idea of whether we live in a simulation, and how does the simulation that we run ourselves, you run in your field, help us do this research and ask the question the other way?
Right. Yeah. So I think the first thing to say is, you know, the idea that we might live inside a simulation is one that's been kind of popularized in recent years through various routes. One of the sort of classic expositions of this idea came about from a philosopher, actually, and he stated that it's in his view, sort of there's a set of options, right? So either if you imagine that in the far future of humanity, we have technology that just continues to increase in its sophistication, sort of far beyond our current day technology, and that we continue to be interested in understanding our history, and therefore we're running simulations. He said, well, then, you know, inevitably, in the end, you get to a level of sophistication in your simulations where you're actually forming living, thinking organisms within these simulations, and then takes the jump to say, well, therefore, why are we should entertain seriously the idea that maybe we are actually inside one of these simulations. Because if those simulations are going to be performed, then how can we rule out that we're not already inside one of them? So that's the sort of statement of the problem. This has been picked up and popularized in various media. And I guess, to be blunt about it, I think it's not correct. I mean, I think the idea is a very interesting one to play around with, but the fact is that if you really wanted to perform a simulation of the universe with the kind of fidelity that we see around us, you know, so if you take seriously that the universe is as rich and detailed as it appears to be, then, to cut a long story short, you would have to use basically the resources of the entire universe to simulate one universe, because otherwise you couldn't build a computer powerful enough to do this. So then the response to that is, yeah, but, you know, maybe the universe isn't quite like that. Maybe the universe it appears to be very detailed to us, but actually it's a sort of fake. When you look out at the universe, at some point, transitions into simplified physics, almost like having CGI scenery for a movie, right? The scenery doesn't exist. And if you start believing that kind of thing, then I think we're in quite a lot of trouble when we start believing in that kind of thing, because then, of course, by implication, or everything we're doing in cosmology is a bit of a waste of time, because it's all a kind of that stuff out there is not real. So first of all, it's a problem for cosmologists, but I think it's also a problem for all of us as humanity, because I think it's creating a sort of level of doubt on the nature of reality that I don't think is really that different from the kind of doubts that somebody like Descartes expressed, for example. Or if you go even further back in history, Gnostic Christianity is based around this idea, actually, the idea that the reality as we experience it is some kind of fake created by some kind of deity who has entrapped us in a reality that's not what it seems. And so to me, this is dovetailing into a set of ideas that is quite antithetical to scientific progress. It's almost like encouraging us just to give up on knowing what's really going on. So you asked specifically about searching for glitches. So an idea that people have is, if we live in this kind of approximate simulated universe, then we could start searching for glitches, things that don't look quite right, things where the simulation's trick that it's playing on us goes wrong. And maybe to tie it to a conversation we had earlier, it's like the subgrid. At some point, the subgrid isn't as accurate as you would like it to be, and so something will just appear very strange. But I think that's, again, a very problematic idea, because unless you specify precisely what you think is going to go wrong, precisely what measurement are we talking about, and at precisely what kind of level of accuracy do we need to get for this to go wrong? It's such an undefined idea that I think it's not something that you can really tackle with a meaningful experiment. You'll just, you may find what you call glitches, or you might not. If you don't find them, then you just say, oh, well, we would need to search in an even more detailed way to find these things. Maybe they're still there. If you do find them, then still I would say, well, maybe this is just pointing to some law of physics we don't yet understand, but it doesn't necessarily say that we're living in a simulation. So this perhaps you've got a slightly longer explanation you're bargaining for there, but I think that's kind of covers in brief why I'm very skeptical about this idea overall, though of course it's kind of fun to explore it.
Yeah, it's a fascinating idea, but I think I also agree that it's kind of difficult to study from a scientific point of view, where you assume that there's some external reality that isn't out there to fool you. Okay, I guess we can start going into audience questions. So Ara Avakin asks, how do we know that the computations and assumptions that lead to the belief in the existence of dark energy and dark matter are not somehow flawed? Could this be hubris in our confidence that we understand the cosmos sufficiently?
I mean, yes, of course, this is the nature of science, right? I mean, science is provisional. And so when we talk about dark matter and dark energy, I think it's always correct to bear in the back of our minds, we don't know that these are real substances. What we can say, as we were alluding to a bit earlier on, is that scientifically speaking, they've been extremely successful ideas, in the sense that they don't just explain away one or two things. They build into a giant framework of observations that we've made about the universe. They've predicted many things successfully. To be fair, they've also got some things wrong as well, that we've then had to go back and scratch our heads and correct and figure out why is that thing coming out wrong. But I think overall, the balance is that they are very, very successful theories. And so then for me, it becomes a practical question of, as a cosmologist, what am I going to spend my time doing? Well, I'm going to work on theory with dark matter and dark energy in it, because it's so far proved extremely successful. I don't take the view that it's therefore impossible to imagine someone could come along tomorrow with a better explanation for all of these phenomena. I think it's a bit unlikely because they're such diverse phenomena, but it's a possibility, and so we keep an open mind. But then we also have to make practical decisions about what are we going to work on, and most people vote with their feet and do work on this kind of dark matter, dark energy centric universe.
I mean, with dark matter and dark energy, they're more defined via their effect rather than their nature. So in the sense that the effect, it's kind of less doubtful that the effect is there.
That's right. So even if something does come along and supplant dark matter and dark energy, it would have to have effects that are very much like them. That's exactly right.
Now, so we would call them that. So then
we might do, or at the very least, you wouldn't just throw away everything that we thought we knew, right? It's you would have a situation where, oh, okay, so this is a better way to think about it. That doesn't mean that everything that came before was invalid. In the same way that, say, Newton's theory of gravity is still incredibly useful and a valid way to think about things, even though we know in reality Einstein's theory is a much more accurate picture of what's really going on.
Yeah, exactly. Okay. What physical equations are you solving in these simulations? Do the equations change depending on the age and scale you're simulating?
Right, so there's a range of equations being solved. I mean, the really central ones are equations of gravity. So that is figuring out the gravitational forces due to one part of the universe on the other. And coupled to that, what we call the laws of fluid dynamics, which are essentially about how gas moves around within the universe and how it behaves if it's squashed or released, or and so on and so on. So those are the sort of the key physical equations that are programmed into the computer. And then, as we were discussing earlier, on top of that, you have these subgrid models, and they often have equations within them, but those equations almost exclusively aren't sort of directly derived from a physical law. They're more like those kind of rules of thumb that we developed over years to try and make sense of the stuff that we can't get at directly.
I don't know if you have time to keep answering more audience questions, but should I keep going on? Or?
I can stay for a few more minutes if you can.
So how do we know dark matter does not have interactions with visible matter other than gravitation?
Chiefly through through what we observe. So for a start, if it did have interactions with matter, then it would have effects. It would have measurable effects, you would assume, on what's going on in, say, our galaxy, but in particular in something called the cosmic microwave background. So the cosmic microwave background is the most ancient light in the universe. As I was saying earlier on, if you look far enough in our universe, you're looking back in time, and you can actually look almost all the way back to the Big Bang itself. And when you do that, you're seeing light called the cosmic microwave background. And the universe then was a very different place, but it had very characteristic ripples in it. So what you really see is it looks like sort of ripples on a pond or something. And the shape of those ripples is very sensitive to the physics of the early universe and whether dark matter is there or not. So it tells us that the dark matter is there, but it's also very sensitive to if the dark matter is pushing on the regular matter in any way, except through gravity, then this would show up in slightly different ripples in the cosmic microwave background. So there are a number of ways you can get at this observationally, and they seem all to point to dark matter having very little in the way of interactions with regular matter. But that's not the same, by the way, as saying that it's zero. It may be that there is some very, very slight interaction with regular matter. And in fact, we hope there is, because that's our key to detecting dark matter for real here on Earth, which would sew up this question of, is dark matter real? There are particles like neutrinos that we do know exist that are very, very hard to detect because they barely interact with the remaining materials. And dark matter may be one of those. Maybe it just interacts at very, very low level, so it doesn't affect any of these things we can see right now. but maybe there is some very small residual force that it can apply other than gravity.
From what reference frame do you observe these simulations output?
Well, we can choose. So there is, I guess there are different sort of levels of technicality within this question. But one of the advantages of having a simulated universe is that you can put a virtual telescope wherever you like within that simulated universe. And you can also simulate what would be the effects of, say, that telescope moving and so on, because we know that motion through the universe changes what we see of it. So you can do all of these things within the simulation, and you get to make choices. And indeed, it's important that we do make those choices. And to go back to the black holes example, for instance, black holes certainly behave very differently depending on whether you're observing them from a distance, for example, or going up close to them. The effects you would see around a black hole look very different indeed. So it's part of the simulation is being able to change your reference point. And maybe one last point to make on that is just that because of what we were talking about this is, being about chaos and the uncertainty in the initial conditions, and so more broadly that this is a bit more like a climate simulation than a weather simulation, there isn't one place in our virtual universe typically that we would say corresponds to Earth. There are places within the simulation that might be somewhat like somewhat like our surroundings here on Earth. But we, in general terms, we don't run simulations where we say, are we going to look at this exactly from the vantage point of Earth, because you can't identify within these simulations something as detailed as our sun, let alone the Earth itself.
Okay, and there are more questions, but I think for the sake of time, we should wrap up. Thank you for this fascinating conversation, and also thank you for writing this great book that I had a chance to read over the past week. Yeah.
Well, thank you. I really enjoyed it.
Thank you both so much for being here. I know I very much enjoyed the conversation and look forward to checking out the book. Have a good day.
Thanks.